Hello, I am Dr. Sigar Kanti, Associate Professor of Mathematics, Government First Year College, KR from Bangalore. In this video, I am going to write a program in Python to verify Lagrange's theorem for finite groups. So we have Lagrange's theorem. If G is a group and H is a subgroup of G, Lagrange's theorem states that order of H divides order of G. Okay. Suppose G is given and H is also given, and if it is confirmed that H is a subgroup of G, then directly we can go for this order of H divided by order of G divided by order of H. If I get this is equal to some integer, then we say that the Lagrange's theorem is satisfied. Order of H divides order of G. Sometimes what happens, if H is not a subgroup, then this is satisfied. For example, if I take G equal to 1 minus 1 I minus I, we know that H is equal to 1 comma minus 1 is a subgroup. Then order of H equal to 2, order of G equal to 4. So that is 2 divides 4 here. That is here order of H divides order of 4. Order of H divides order of G. Okay. So suppose H is not a subgroup, then first we have to verify that H is a subgroup of G, and then we go for this order of H divides order of H. Okay. For that, we have necessary and sufficient condition. A non-empty subset H of a group G is a subgroup of G if and only if we have A comma B belongs to H, implies that AB inverse belongs to H. Okay, this is the necessary and sufficient condition. Or one more necessary and sufficient condition is A comma B belongs to H, implies that AB also belongs to H. That is closure law satisfied in H. And one more condition is if A belongs to H, implies that A inverse also belongs to H. That is the inverse axiom. If inverse axiom satisfied and closure law is satisfied in H, then we say that H is a subgroup of G. So first what I do here is I will check whether that H is a subgroup of G or not. So for that what I do here is first I will verify this, that is whether inverse of each element exists or not. So that is here A inverse belongs to H means if I take SC H inverse, that is this is the set of inverses of A, then definitely we have H inverse is equal to H. Okay, if we inverse of each element exists, then we get H inverse equal to H. And second one, this the closure law. So that is here if A comma B belongs to H, implies that A into B also belongs to H, then we say that H is a subgroup of G. So first I will go for this one, whether H equal to H inverse or not. If H equal to H inverse, then I will check the closure law. Then we decide that H is a subgroup of G. Then I will go for the Lagrange's theorem, order of H divided by order of G. Okay. So for that, I will go to, first I will write a comment line here. Verification of Lagrange's theorem for finite groups. Okay. So here I will take one example. I'll take an example. The example is I'll take G equal to group 1 comma minus 1 comma I comma minus I. That is the fourth roots of unity with respect to multiplication. Okay, and I'll take H is equal to 1 comma minus 1. We know that this is a subgroup. I will check this Lagrange's theorem. So here what I do is I will write G first. G equal to set 1 comma minus 1 comma I is 1j comma minus I is minus 1j. Okay, this is our G, and H is equal to 1 comma minus 1 comma minus 1. Then to find the inverse of each element of H, and we place in some other set, I will denote that set by say S. I will make one set, empty set, that is S is the set consisting of no elements here. This is an empty set. And after finding the inverses of each element of this H, I will place those elements in S. Okay. So this is okay. Now I am going to find the inverse elements of H. So for that I will use for loop here. For A in H colon, for B in H colon, if A star B equal to the identity element. So in this case the identity element is equal to 1. If we get A star B equal to 1, then B becomes the inverse of A. Okay. Again on colon, what I do here is I will keep this I will include this B into this set S. Okay, that is S dot update S dot update B. Okay, S dot update B. Then so that we are finding the inverse of each element of H here. That is inverse of A. B is the inverse of A. Now finally, after finishing these two for loops, S becomes the set consisting of inverses of each element of H. Okay, so that is our H inverse, right? We can print this. Print yes. Okay, we can print this yes, and then we'll take one variable name here. Say I say SG, that is any variable. I have taken this as SG, that is for subgroup. I have taken SG equal to 1. I will assign that SG equal to 1, and then if this H is equal to S, that means S means this is nothing but H inverse. Okay, that is S is the inverse elements of H. If H equal to S, that is H equal to H inverse. H equal to H inverse, then so that means here I got the first one here, H equal to H inverse. If I get H equal to S inverse, then I will go for the closure law. Okay, I will go for the closure law. If H equal to S, then go for the closure law. For A in H colon, next for B in H colon, okay. Now here if A star B not in H, then closure law is not satisfied. So that is closure law is satisfied if A star B also belongs to H. Suppose A star B does not belong to H, then closure law is not satisfied. I have taken that this SG, that it is a subgroup. So if the closure law is not satisfied, then just a minute. So if closure law is not satisfied, then what I do here is I will make this value of SG equal to 0. So I have taken Hg equal to 1. If closure law is not satisfied, then Hg becomes 0. Otherwise, Hg value is equal to 1 itself. And then suppose Hg equal to 1. Suppose Hg equal to 1. So I will be in the first if here. If H is equal to S, and then if closure law is satisfied, then Sg is equal to 1. Okay, Sg value equal to 1. So what I do here is if Sg equal to 1 means it is a subgroup. It is a subgroup. Then I will verify the Lagrange's theorem. So that is Lagrange's theorem is if order of G by order of G percent order of H equal to 0. That is, if order of H divides order of G, then length of G by length of H must be equal to 0. Okay. So that means here H order of H divides order of G. If length of G by length of H is equal to 0, again we have to put a colon here, then we give a print statement. Print Lagrange's theorem. Lagrange's theorem is satisfied. Is satisfied. Okay. Else I have to write in this if line. Else, that means here if order of H is not dividing order of G, then we write print Lagrange's theorem is not satisfied. This is never going to be executed because Lagrange's theorem, we have Lagrange's theorem. If H is a subgroup of G, definitely divides. Okay. Now, after this, if Sg, I take okay, write this in. I'll make one indent. Okay, so this is when if H equal to H inverse and the closure law is satisfied, that again I have taken if Sg equal to 1, closure law is satisfied, then we have verified this one. Else, so here if Sg equal to 1 means H is a subgroup of G. If Sg is not equal to 1 means H is not a subgroup of G. So here I will write else print H is not a subgroup of G. Okay. So this is printed. Suppose H equal to S. That means here H equal to H inverse, and closure law is satisfied, then this is executed. If H equal to H inverse and the closure law is not satisfied, then this is executed. Okay. Next I will give one more else. That else is for this one. Okay. If H is equal to S, then these are executed. If H is not equal to S, that is else H is not equal to H inverse, then again it is not a subgroup. That is print H is not a subgroup of G, then there is no question of verifying the Lagrange's theorem. Okay, so let me run this program. I think everything is correct. G I have taken 1 minus 1, J minus J, H equal to 1 minus 1, S is the empty set for A in H, for B in H, A star B equal to 1, B becomes the inverse of A, and I am updating that yes, that is including B in S. Now finally, after coming out of these two for loops, our S is nothing but the set of all the inverse elements of H. Then I am assigning Sg equal to 1. I am defining one variable name here, Sg equal to 1. Then after this I will go that if H equal to S, that means H equal to H inverse, then this is the part which verifies the closure law. If closure law is not satisfied, then Sg value becomes 0. Otherwise, Sg value equal to 1. So next, after this one, within this H equal to S, if this is true, then again I will, if Sg equal to 1, that means closure law is satisfied and inverse law is also satisfied, then I will check. That means this H becomes a subgroup of G. I will verify the Lagrange's theorem here. Else means Sg is not equal to 1. Sg is not equal to 1 means that the closure law is not satisfied. Therefore, okay, this else is for, this else is for this if. That is, this is order of H divided by order of G. Okay, if this is not equal to 0, then Lagrange's theorem is not satisfied. And we have this else here. This else is for this if. Sg is not equal to 1 means closure law is not satisfied. Then we print H is not a subgroup of G. Again, this else is for this if. That is, if H is not equal to H inverse, again we print H is not a subgroup of G. Okay. So let me run this program. So this given the print statement for S is equal to 1 minus 1. This is inverse of H. And Lagrange's theorem is, okay, I'm sorry, something is wrong. If Sg equal to 1, length of G by length of H is equal to 0, Lagrange's theorem is satisfied. Else print Lagrange's theorem is not satisfied. If Sg equal to A in H for B in H, if A star B not in H, then I am making this Sg is equal to 0. Okay, if Sg equal to 1, and within that if length of G by length of H is equal to, sorry, I have write this percent, make this as percent. So that means here remainder obtained when this length, the order of G is divided by order of H. Okay. Now run this program. Yeah. This is our H inverse. Lagrange's theorem is satisfied. Now let me change the subgroup here. So instead of this 1 comma minus 1, if I go for 1 comma say 1j. Now this is not a subgroup here. But order of H divides order of G. But H is not a subgroup. Then I have to get the output as H is not a subgroup. Okay, running this program. Everything is same. Only I have changed H here. So I am getting, and here inverse of that J does not exist. We know that inverse of J means inverse of I is equal to minus I. That minus I is not there in H. Okay. So that means I am getting H inverse equal to this one. H is not a subgroup of G. H is not equal to H inverse here. Now if I go to this is, I will make minus 1j. I have taken I and minus I here. Inverse of j I is minus I. Inverse of minus I is plus I. Okay, here H equal to H inverse, but closure law is not satisfied, because if we take these two elements here, multiplication of these two elements, I into minus I is minus I square, that becomes plus 1, but plus 1 is not here. That closure law is not satisfied. H equal to H inverse I am getting, but closure law is not satisfied. Therefore, H is not a subgroup of G. Okay, run this program. Yeah. I am getting H equal to H inverse, but closure law is not satisfied. Therefore, H is not a subgroup of G. Now, let me go for another example. I'll go for another example. I'll take G equal to 0, 1, 2, 3, 4, 5. We know that this is a group with respect to addition modulo 6. Okay. And I'll take H is equal to 0, comma 2, comma 4. I think this H is a subgroup of G with respect to addition modulo 6. Now, everything will be same. Only thing I have to change the operation here. Instead of star, I have to write this as plus. Okay. Addition modulo 6. A plus B percent 6 equal to. Here I have to write the identity element. Here in this case, identity element is not 1. It is equal to 0. Okay. And then rest of the things will be same. Here I have to change the operation. If A plus B percent 6, my operation is addition modulo 6 is not in H, then SG becomes 0 and the remaining thing is same. Okay. Yeah. Now I will run this program. I am getting H inverse equal to 0 to 4 same. Lagrange's theorem is satisfied. The closure law is also satisfied. Therefore, Lagrange's theorem is satisfied. H is a subgroup of G and the Lagrange's theorem is satisfied. Next, I will go to another example. I will change the sets here. I will change this set as G equal to 1, 2, 3, 4, 5, 6. This is a group with respect to multiplication modulo 7. Okay. And here I will take the H as 1, 2, 4. I think this H is a subgroup of G. And our operation is multiplication modulo 7. So I have to change the operation here. This I have to make star. This I have to make 7. And this will be same. Here also I have to change. This is star. This is 7. Okay. I think rest of the things will be same. Okay. Now I run this program. Running this program. H is not a subgroup. I am getting set. Okay, just a minute. G equal to H equal to 1 to 4. S equal to empty set. A in H, B in H. A star B percent 7. Okay, update B. This is okay. H equal to S. Here also I have A star B percent 7. Am I getting H is not a subgroup. This 1, 2, 3, 4, 5, 6. 1, 2, 4. 1, 2, 4. 1, 2, 4. A in H, B in H. Okay, everything is correct, I think. A star B percent 7. Okay, I have to make. Yeah, in this case, identity element is not 0. Identity element is 1 here. Okay, I have to make this as 1. Then, okay, remaining thing is same. Now running this program. Yeah, 1 to 4. H equal to H inverse. Lagrange's theorem is satisfied. Now I will go to another example. 2, 4. I will go to this example. 2, 4, 6, 8. This is a group with respect to multiplication modulo 10. Here I will take H. H as 4 and 6. 4 comma 6. I think this 4 comma 6 is a subgroup, and here the identity element is 6. Our operation is multiplication modulo 10. So here I have to make this 7 as 10, and this 1 identity element is 6 here, and here also I have to change the operation, multiplication modulo 10. Remaining thing will be same. Okay, now let me running this program. Yeah, H inverse equal to 4 6, same. Lagrange's theorem is satisfied. I'll go to another example. So I take the same group here, but I'll change H. I'll make H is equal to 2, 2 comma 6. Identity is there. Identity is there. And instead of this 4, I have taken 2. Then if I run this program, what happens? The remaining thing will be same. Okay. Yeah. See here, H is not equal to H inverse. Okay. Inverse of 2 does not exist there. Inverse of 2 is 2 into 4, 8, 2 into 8, 2 into 8 is 16. Yeah. 2 into 8. Inverse of 2 equal to 8. But that 8 is not here. And in the previous case, I had taken 4 comma 6. Inverse of 4 was 4 itself. Right? 4 into 4 is 16. Divided by 10, I am getting the identity element. So in this case, H is not a subgroup of G. Okay, thank you. I'll stop here.